Okay, so when you are doing the change of variables, one of the 3 steps is to change the differential dA. So instead of using dA equals dx dy, you need to use dA equals something times du dv. So how do you find this unknown something here? I'm going to give you 3 ways of finding dA in the new variables. The first way is going to be by geometrical intuition. So this means that you literally draw the grid. So draw or imagine the grid in the new variables and find the size of dA, or the size of a square of the grid. Let me call it with a proper name, a parallelepiped, which is the more general case of the grid. So for instance, when you are in xy coordinates, you draw a grid of constant x and constant y, so then it's very easy to find that if you do delta x times delta y, or let's call them directly as if they were differentials, yeah? So dx and dy. So it's very easy to see that dA is equal to dx times dy. That is the area of one of these squares, okay? But when you change variables, you are changing the way you split the region. So for example, if you are using polar coordinates, so you are using rho and phi. So the lines of constant rho are circles like this. So here is the origin. And the lines of constant phi are radial lines like this. Yeah. So now you need to find the area of one of these elements, which in the limit, when so this would be d rho, the change of rho, and this would be d phi, right? The change on the angle phi. So in the limit, when d rho and d phi go to 0 because they are differential, this forms a parallelepiped. In this case, it would be a rectangle, and this rectangle will be d rho in this direction, and the size in this direction will be rho times d rho, because you have to multiply the angle times the radius, right? So that would give you that dA is equal to rho times d rho times d phi. Okay, so by geometrical intuition, you can figure out the value of dA. Second, you can follow a recipe. And this recipe, surprise, surprise, uses your old friend, the Jacobian determinant. Remember, I presented you to the Jacobian determinant in the previous chapter about partial differentiation. So follow the recipe using the Jacobian determinant. And let me write that recipe for you. The new dA is equal to the Jacobian determinant of x and y with respect to u and v, where x and y are the old variables and u and v are the new variables, times du times dv. So remember that this Jacobian determinant, let me write it, sometimes it's often just called the Jacobian, and this is equal to the determinant of a matrix, where this matrix is formed of the partial derivatives of x with respect to u, x with respect to v, y with respect to u, and y with respect to v. So you find those partial derivatives, and then you find the determinant, and that's what you have to place here. Okay, so that's a recipe that will always work. And finally, the third method, and this is usually the one you will use most often, you look it up. This is good news, right? So let me tell you what I mean by this. If you go to Kits page on our module, on general material, you have the reference list of equations. And this reference list of equations has a convenient, very convenient table, which I will tell you how to use, but basically, for example, if you are looking for the differential of area, so you have to look at this column here, and this is written for cylindrical coordinates, but you know that polar coordinates are basically cylindrical coordinates without the z component, okay? So if you get rid of the z component, then this z goes to 0, so this goes to 0, this goes to 0, so you end up only with this. So you end up with rho times d rho times d phi. So this is the differential of area in polar coordinates, which is exactly what we also derived here from geometrical intuition, okay? So you look it up in the table. So table provided in list of equations. So as you have noticed, this table has lots of other things that you still have no idea what they are, like the differential displacement, the differential S that here I'm saying it's a vector, I will talk about that later, and the differential of volume. So we will talk about all these things later, but know that the most common way of finding the differential is by looking it up in this table, okay? Because most of the times the change of variables that I'm going to ask you to do is going to be cylindrical or spherical coordinates, okay? So that's all. Let's see examples of the 3 ways of doing this. Thanks for watching. See you in the next video.